So, have you ever thought about how our power grids actually handle it when cities just keep growing and growing? When demand for electricity goes through the roof? Well, a huge part of the solution is this really clever engineering move, running massive transformers in parallel. It's kind of the secret sauce for making a grid that's not just powerful, but also super efficient and reliable. And today, we're going to dive deep into the specific rules that make this whole power sharing thing work.
All right, so here's the game plan for this explainer. We'll kick things off with why we even do this in the first place. Then we'll get into something called the polarity test. It's super critical. After that, we'll break down the rules for both single-phase and three-phase transformers. We'll also cover what happens when you mess up, the cost of mismatch. And we'll wrap up by looking at the actual physics behind how the load gets shared.
Okay, so first up, why bother with all the hassle of connecting two transformers? I mean, why not just get one giant one and call it a day? Well, as it turns out, the answer is all about solving a really interesting efficiency puzzle.
So, let's put you in the driver's seat. Imagine you're running the power grid for a city that's booming. Every day, more people, more buildings, more power demand. What do? Do you just tear out the old transformer and drop in a single massive new one? Or is there a better, smarter way to handle that growth?
Okay, check this out. That single huge transformer, it's great when everyone's got their AC blasting on a hot summer day. But what about at 3 a.m. on a Tuesday? It's basically running on a super light load, and that's just inefficient. It's like using a monster truck for a quick trip to the corner store. You're just wasting a ton of energy as heat. The much smarter play is to use parallel transformers. You can have one unit handling the normal, everyday load, and then, boom, you switch on the second one only when you need it for those peak hours. It's way more flexible, it's scalable, and it's just so much more efficient.
All right, so we've got the why down. Now let's get into the how. And listen up, because this next part is a huge deal. Before you even dream of connecting two transformers together, there is one test that is absolutely 100% non-negotiable. It's called the polarity test. And trust me, you get this wrong, and you're going to have a very, very bad and very expensive day.
So what is polarity anyway? Well, with AC power, the voltage is flipping back and forth constantly, right? Polarity is basically just a way to label the plus and minus ends of the windings at any single frozen moment in time. And for a parallel connection to work, you absolutely have to connect the terminals that are hitting plus at the exact same instant. They have to be in sync. And the polarity test, that's how you figure out which terminals are which.
And the test itself is actually pretty simple. You start by connecting the primary and secondary windings together in a series loop, then you feed some AC voltage into one of them. The last step is to take a voltmeter and measure the voltage across the two open ends. Now, here's the moment of truth. If your voltmeter shows you the difference between the two voltages, like E1 minus E2, then bingo, you've got subtractive polarity, everything's marked correctly, and you're good to go. But if it shows you the sum of the voltages, E1 plus E2, that's a red flag. It means you have additive polarity, and one of your labels is backwards. You've got to fix that before you do anything else.
But why the big deal about subtractive polarity? Why is that the one we want? Well, it all comes down to safety. The entire industry prefers it for a really important reason. With subtractive polarity, you avoid having a huge voltage difference right between two terminals sitting next to each other. By keeping that electrical stress low, you're massively reducing the risk of things like the insulation failing or electricity arcing across, which, yeah, that's bad. It makes the whole setup safer and much more reliable in the long run. And you know what's really cool? This isn't just some old-school test they did back in the day. Even now, with all our fancy, powerful computer software like Simulink, engineers are still running simulations of this exact same polarity test. They do it in the virtual world before a single piece of real hardware gets built. It just goes to show you, this is still a rock-solid, foundational part of safe transformer design.
Okay, so you've nailed the polarity test. It's correct, it's subtractive. Awesome. But hold on, you're not ready to flip that big switch just yet. When it comes to single-phase transformers, there are a few more things you absolutely have to check off the list. First, like we said, polarity has to be the same. No question. Second, their voltage ratings need to be pretty much identical. If they're not, you'll get this big, useless current just circulating between the two transformers, wasting energy. Third, and this is kind of a no-brainer, their combined power rating, the kVA, has to be more than the load you're trying to power. And last but not least, their R to X ratio should be the same. That's the ratio of their internal resistance to their reactance. If these match, they'll share the load perfectly, which stops one of them from getting stuck with a bad power factor. All right, now let's level up. Things get a little more complex when we move from single-phase to the three-phase systems that basically run our entire power grid. All those rules we just talked about, they still apply, but now we've got to add 2 more super important conditions to our checklist.
First step is something called relative phase displacement. Basically, it's got to be 0. This just means the output voltages of the 2 transformers have to be perfectly in step with each other with no time lag or angle difference. Engineers call this making sure they're in the same vector group. If you mix and match groups, it just won't work. The second rule, though, is even more serious. The phase sequence must be identical. We're talking ABC on one has to match ABC on the other. If you get this wrong, say you connect phase A to phase B, it's not just a small problem. It's a direct, massive short circuit. The result is instant, and it is not pretty.
So we've gone through a whole bunch of rules here, but what actually happens if you break them? What are the real-world consequences when you don't check all these boxes? Well, the cause and effect is pretty clear. If your voltage ratios don't match up, you get that circulating current we talked about, just pointlessly generating heat and wasting power. If the R to X ratios are different, the transformers won't share the work fairly based on their size. You could have one transformer getting dangerously overloaded while the other one is just coasting along, barely breaking a sweat. And yeah, like we just said, if you screw up the phase sequence on a 3-phase system, it's game over. You've created a dead short, which could lead to a catastrophic failure and take out power for a whole area.
Okay, for our last section, let's peel back the curtain a little bit and look at the actual physics behind how these transformers divvy up the work. It really all boils down to one single key property.
And that property is called impedance. You'll see it written as the letter Z. Put simply, impedance is just the total opposition that the transformer puts up against the flow of alternating current. Think of it like the total friction inside a pipe. It's a mix of good old-fashioned resistance and another thing called reactance, which has to do with the magnetic fields inside. This number, impedance, is the key to understanding how the load is shared.
And the formula that governs this is actually pretty elegant. The load on transformer 1 divided by the load on transformer 2 equals the impedance of transformer 2 divided by the impedance of transformer 1. See that? The numbers are flipped. 1 over 2 on the left, 2 over 1 on the right. That's the whole secret right there. It tells us that the load sharing is inversely proportional to the impedance.
So what's the bottom line here? It's simple. The transformer with the higher impedance does less work. That's it. You can think of electricity like water. It's always going to follow the path of least resistance, or in this case, least impedance. So the transformer with the lower impedance is the one that's going to take on more of the load and do the heavy lifting. And that's exactly why getting their impedances matched is so important if you want them to work together nicely.
And all this brings us to a really interesting thought about the future. Our power grids are getting smarter all the time. So what if automated systems could just handle all of this? Imagine a system that could check the polarity, the voltage, the phase sequence, all of it in real time. Could we use smart grid tech to totally prevent these kinds of dangerous and expensive mistakes before a person even gets near the switch? Well, that's exactly the kind of thing engineers are working on right now.